Allow yourself a moment to find a comfortable position, whether sitting or reclining, and gently close your eyes if you wish. Feel the weight of your body, the steady pace of your breathing, and allow your thoughts to wander freely. Now, imagine that your thoughts could break free from the anchor of the present moment. Picture them drifting beyond the boundaries of what we usually call today, as though they could step back into days long past or surge ahead to moments not yet formed. This is the essence of time travel, a notion both deeply familiar in the sense that we all experience time's forward march, and yet thrillingly alien because our everyday lives are bound by a strict chronology that never deviates or rewinds. By contemplating the possibility of moving through time at will, faster, slower, or even backward, we invite ourselves into a realm of reflection and curiosity. And as we embark on this journey together, let the pace of your own internal clock slow down and let the whisper of possibility grow ever louder. Time travel, in the broadest sense, is the hypothesis that we can experience the dimension of time in a manner different from the ordinary sequence of events. This can manifest in many ways. It might imply living more swiftly than those around us, so that years pass for others, while only moments pass for us. It might evoke the idea of slowing our personal timeline, outlasting entire generations yet hardly aging ourselves. Or perhaps most tantalizingly, it could open a door to the past, allowing us to revisit days gone by and walk once more among the details we thought had slipped beyond reach. And in a more speculative sense, it might let us peer into the future, glimpsing outcomes that haven't yet taken shape in our current reality. When we talk about time travel, then, we are speaking of changing our velocity relative to the passage of time, or even reversing that fundamental current, an endeavor that collides head-on with the laws and limitations of the universe as we understand them. Before we delve further, let us recall the moment when the idea of time travel first captured the public imagination. While human beings have likely always wondered about the possibility of revisiting their past or looking ahead to their future, one of the most iconic early explorations of this concept appears in literature, specifically in science fiction. Authors from centuries past, even in older mythologies, toyed with the notion of stepping outside of one's time, yet it was the rapid progression of modern science and industry in the 19th century that provided fertile ground for these dreams to take more definite shape. H.G. Wells, in his novel The Time Machine, published in 1895, gave readers a story in which a marvelous contraption whirled its occupant to eras far removed from his own. This fresh perspective captured the imagination of a society already enlivened by the wonders of the Industrial Revolution. Trains racing across landscapes, telegraphs sending messages across oceans, and the beginnings of automobiles replacing horse-drawn carriages. Wells offered a narrative in which we weren't restricted to conquering physical distance alone, but could also transcend the boundaries of time. From that literary spark, ideas about time travel began to flourish in both scientific and popular culture. Modern theoretical physicists have delved into concepts such as wormholes, tunnels in the fabric of space-time that might connect distant points and distant times, as well as the possibility of faster-than-light travel, even though our current understanding of physics places stringent limits on such aspirations. Albert Einstein's theories of special and general relativity revolutionized how we understand time, space, and gravity, revealing that time can bend, stretch, and fold in ways that defy our everyday intuition. The idea that we can manipulate this malleable fabric of existence, however, remains firmly in the realm of hypotheses, thought experiments, and occasionally the dreamscapes of fiction. Yet the allure of such concepts remains powerful. Each new development in physics, each new puzzle about the nature of reality, rekindles the question, is there a method we have yet to discover that would make time travel a reality? By considering time travel, we also invite ourselves to contemplate the deeper mysteries surrounding causation and consequence. If one could go back in time, what would that do to the delicate web of cause and effect that underlies our universe? Would changing a single detail, like stepping on an insect or preventing an accident that originally led to a crucial invention, result in a different future that ripples outward to reshape history? Or is there a broader harmony in the universe that resists such alterations, ensuring that events unfold in a predetermined manner, no matter how we might try to intervene? These questions inevitably lead to discussions of free will. Do we truly have the capacity to alter our destiny? Or are we following a script already written by the fundamental laws of nature? And if time travel is possible, does it bring with it the power to rewrite that script? Or would we simply discover that our attempts to make changes were always woven into the tapestry of events from the start? One of the most striking dimensions of time travel is how it compels us to reconsider the very flow of time. We often take it as a given that time marches forward at a steady pace, as unyielding as the ticking of a clock. From the moment we open our eyes each morning until we sleep at night, we assume a progression of events. The sun rises, we live our day, and the sun sets. The next day follows the same pattern, yet a closer examination of physics reveals that there is no universal, absolute clock ticking away in the universe. Instead, time is intimately tied to our frame of reference. A person traveling at near the speed of light might age more slowly relative to someone staying on Earth. This phenomenon, verified through experiments and satellites, is a real effect known as time dilation. But beyond these tested aspects of relativity, we step deeper into speculation when we imagine a scenario in which we can hop from one point in time to another. We start to ask, if there is no universal now, then what truly demarcates past and future? Why do we perceive ourselves being swept along a single directional current from yesterday to tomorrow, when the laws of physics appear to allow for more intricate relationships among events? Such reflection can be disorienting, and that sense of mystery of the unknown is part of what lends time travel its perennial allure. Even the greatest scientific minds often admit that we do not yet have a definitive theory to explain how time truly operates at every level of reality. Quantum mechanics, with its probability waves and uncertainty principles, doesn't fully align with the smoother, continuous flows suggested by relativity theory. So we're left with puzzles like Schrödinger's cat, wave functions, the search for a theory of quantum gravity, and the suspicion that time might behave in ways we have yet to fully conceptualize. That gap in our understanding is precisely what nurtures the imaginative leap into time travel tales. The wide, unexplored terrain of cosmic theories leaves room for countless possibilities, including those that might seem to border on fantasy. But time travel also speaks to something deeply human, our longing to revisit memories or to peer ahead into uncharted days. Think about the weight of regret or the warmth of nostalgia. How often have we wished we could say one more word to a loved one who has passed on, or witness a historical event firsthand, or even fix a mistake that has haunted us through the years? The concept of traveling back in time resonates with our desire for closure, our craving to fully understand the events that shaped our lives. And what of the future? How tempting it is to see how our lives will unfold, how the world around us will grow and change, and whether humanity will resolve its current challenges or find itself in deeper unknowns. This emotional connection to time travel is precisely what invests it with such a potent mixture of excitement and, in some cases, trepidation. Because if the future holds both wonders and catastrophes, can our knowledge of it change the course of what is to come? Yet even amidst all these grand speculations, there is a deep sense of wonder, like standing at the edge of a vast ocean, gazing out into the horizon where sky and sea meet. We know that as our understanding grows, the boundaries of the possible may shift. The unknown looms like an uncharted territory, beckoning us onward with the promise of discovery. Time travel occupies a special place in that territory, uniting scientific exploration with philosophical inquiry and emotional resonance. It is a testament to the vastness of human curiosity that we continue to return to this concept, generation after generation, whether in novels, films, academic papers, or quiet midnight musings. In many ways, time travel is also about storytelling, weaving narratives that allow us to inhabit alternate worlds, parallel timelines, or reimagined realities. Through these stories, we confront paradoxes and illusions that challenge our intuitive sense of logic. What happens if you travel back in time and prevent your own birth? If you meet a future version of yourself, how does that interaction reshape who you become? Does the simple act of observing a past event transform it? These paradoxes unsettle our usual notions of chronology and underscore the complexity of any attempt to step out of the familiar stream of time. Indeed, these questions have become a central motif in science fiction and cultural discourse, turning time travel into a seemingly inexhaustible source of fascination. Now, gently turn your attention to the concept of paradoxes themselves, which we will soon explore in greater detail. Consider how paradoxes function like playful riddles for the mind, requiring us to look at reality from angles we may have previously overlooked. They highlight the fragile structures of cause and effect, reminding us that even seemingly concrete ideas can melt away when we venture into extreme thought experiments. While it might feel unsettling to confront these contradictions, it can also be tremendously freeing to realize that our understanding of time and reality is not locked in place, but rather open to new perspectives and creative discoveries. Paradoxes then become the pivot around which many time travel narratives revolve. They serve as cautionary tales, moral lessons, and intellectual challenges, illustrating just how peculiar and mysterious life could become if we're ever able to traverse temporal boundaries. The beauty of paradoxes lies in their ability to both reveal and obscure. They shine a light on the hidden assumptions within our logical frameworks, even as they may lead us to question the very nature of those frameworks. As you prepare to move from this initial exploration of time travel into a deeper engagement with the paradoxes that define it, allow yourself one more moment to dwell in your own personal sense of time. Feel the memories rising in your mind, the images of people, places, and experiences that carry emotional weight. Envision the potential future you long for and the one you might fear. Reflect on how these images shape your present identity, your choices, your sense of purpose. Indeed, in the very act of recalling the past or imagining the future, you're experiencing a tiny hint of time's fluidity. Your consciousness shifts momentarily into recollection or anticipation, bridging the gap between what was and what could be. How can something be both true and not true? How can we both exist and not exist? These are the riddles that arise when we dare to toy with the linear nature of time. They challenge our capacity to reason, inviting us to expand our minds and grapple with the full strangeness of a universe that may be more flexible than it first appears. So with that said, let us hold on to our sense of calm curiosity as we set our sights on these mind-bending puzzles. Paradoxes are the riddles that give time travel its allure, forcing us to accept that once we step outside the usual temporal flow, all manner of strange possibilities unfurl. As we continue this journey, keep in mind that these puzzles are not merely mental exercises, but windows into the deeper structure of reality. After all, by wrestling with them, we might be learning how to peek behind the curtain of our everyday perceptions and see time for what it really is. For now, let your imagination rest lightly on the idea of stepping into your own memories, feeling the warmth, the tension, the laughter, the pain that once was, and consider the prospect that time might be a tapestry of interwoven moments rather than a single arrow heading inexorably forward. And with that gentle reflection, we prepare to unravel the enigmas of paradoxes that lie just ahead. Take a moment to let your breath find a gentle, steady rhythm. Settle into a posture that allows you to feel relaxed, yet alert. Imagine, if you will, that the boundaries of time have just loosened around you. Instead of marching forward from yesterday to today and then onward to tomorrow, time begins to reveal gaps, loops, and hidden doorways. Slowly, you step through one of those doorways, directly into the past. You arrive in a world predating your own birth, perhaps decades before you first drew breath. As you acclimate to this altered timeline, you realize a critical possibility lies within your grasp. You could prevent your grandparents from ever meeting, thus erasing the very lineage that led to your existence. If you chose to do so, what would become of you? Could you stand there fully real and tangible once that act severed the thread of your ancestry? This confounding situation is known as the grandfather paradox, a famous thought experiment that challenges our assumptions about cause and effect. To understand the grandfather paradox more intimately, first conjure an image. You are perched on a sturdy tree branch, gazing out at a tranquil forest scene. The sun filters through the leaves and the air feels calm and safe. But if you were to take a saw and cut the very branch on which you are sitting, you would plummet to the ground. That moment, the instant of severing the branch, mirrors the self-defeating nature central to the grandfather paradox. The act that sustains you, your birth, has in this scenario been undone by your choice to meddle in ancestral events, leaving no logical path for you to continue existing in the timeline where you committed the act. At its core, the grandfather paradox explores the tangle of causal relationships. Under normal circumstances, we accept cause and effect as straightforward. An event cause leads to an outcome, effect. However, When a time traveler journeys to the past and disrupts the chain of events that would have allowed them to exist, they introduce a contradiction. If your grandparents never meet, then your parents are never born, which means you cannot possibly exist to travel back and orchestrate their non-meeting in the first place. And yet, here you are, interfering. The mind can tie itself in knots, trying to untangle these competing realities. This paradox hinges on the assumption that our universe operates under a linear timeline. The past influences the present, which in turn shapes the future. We tend to believe that once something has occurred, it remains fixed in the past, etched into history. But time travel scenarios challenge this very notion. If the timeline is malleable, if the past is subject to alteration, then we must ask, how can we consistently preserve a single, unbroken story of events? Once your actions revise the course of history, the original timeline that gave rise to your journey might evaporate like a dream, leaving you standing in a reality that cannot logically exist. This riddle, the ultimate puzzle, has fascinated philosophers, scientists, and writers for decades. Consider, for instance, how we experience our own life story. There is a chain of ancestry behind each of us. Parents, grandparents, great-grandparents, stretching back through the centuries. Each branch of that family tree was shaped by countless coincidences, choices, and historical moments. In your everyday life, you probably don't think much about your grandparents' first meeting, but it was a pivotal event for your lineage. Without it, neither you nor many of your relatives would be alive today. Now imagine that you not only think about this meeting, but actually appear there just before it occurs and intervene. Perhaps you prevent them from crossing paths or say something that sours their relationship. Whatever you do, you make certain they never become a couple. In that moment, you've changed the fundamental structure of your own past. The future that depended on their union can no longer exist, at least not in any way that includes you. So how can you still be standing there, the orchestrator of this change? One perspective suggests that the act of traveling back in time and interfering triggers a new branch of reality. You create an alternate timeline in which your grandparents never met, one that is distinct from the original timeline you departed. In that alternate timeline, you indeed do not exist. But the you who stands there must have come from the original timeline, meaning that two versions of history now coexist, one in which you were born, allowing you to become a time traveler, and another in which you never come to be. If these two timelines can somehow remain separated, perhaps you persist in your own thread of reality, even though you've made changes to another. This idea appears frequently in science fiction, easing the paradox by allowing multiple, branching realities to unfold independently. The notion that these could serve as time machines arises when we consider how relativity merges time and space. Imagine a wormhole with two mouths, each positioned in a different frame of reference. Perhaps one mouth is placed near a massive object, such as a star, where gravity is extremely intense, and the other mouth remains far away from such gravitational influence. Or one mouth travels near the speed of light, the other remains at rest relative to some observer. According to relativity, clocks run differently under gravitational fields or velocities. Time can slow down in conditions compared to a region with weaker gravity or lower speeds. Thus, the two mouths of the wormhole may no longer be synchronized. You could enter one mouth and exit the other at a point in time that differs from the point you left, effectively enabling you to jump forward or back relative to some outside observer. Yet for all its mesmerizing promise, the concept of wormhole travel raises practical and theoretical challenges. First and foremost is stability. The equations that describe wormholes, they might almost instantly upon formation, pinching off before anything can through. To counteract that, exotic matter with negative energy density would be required to push back against gravity and keep the tunnel open. The problem is that such exotic matter, while theoretically proposed in certain processes, has been harnessed in a way that would allow large-scale engineering of space-time. The energy requirements are lowering beyond any technology we currently understand. To lift an entire mountain range with just your bare hands, the scale of energy needed to maintain a stable wormhole is so vast that it has led many physicists to doubt that wormholes could ever become practical modes of travel. Even if the stability challenge were overcome, the possibility of time travel paradoxes. We might think back to the grandfather paradox and realize that a wormhole as a time machine could create similar logical loops. Emerged from a wormhole in the past, you might change events in ways that undermine your decision to travel back in time, creating contradictions. This puzzle suggests that if wormholes do permit time, reality might enforce certain restrictions on what travelers can do, or else time travel might prove impossible in what we understand. Still, the human imagination is drawn to what wormholes represent, a potential liberation from the constraints of distance and chronology. Perhaps there is a universe in which cosmic civilizations have harnessed such tunnels, shortcuts between star systems, and weaving networks of commerce and knowledge, space and time. These ideas are remnant of the final frontier spirit in humanity's drive for exploration. Wormholes, in that sense, could be viewed as cosmic highways, bridging unimaginable gulfs and enabling us to see corners of the universe remain inaccessible by any means. Our comprehension of the universe expands and evolves, yet we remain of finite perspective, reliant on instruments and theories that are constantly refined. There's a kind of peaceful acceptance in acknowledging that some of the universe's deepest secrets may lie beyond our current scope of knowledge. Wormholes like black holes, dark matter, or quantum phenomena remind us that reality can be more fantastic than we dare to dream, pressing us to keep asking questions, keep building telescopes, keep writing equations, and keep imagining possibilities that challenge our intuition. There's also a meditative quality in contemplating these vast distances and the tunnel that might link them. Picture yourself inside the walls of space-time curving around you like silk drapes, shimmering with the light of distant stars. Moving, the journey is strangely calm, as if you're gliding a gentle current. In an instant, assuming all goes well, you emerge into an entirely different region of cosmos, where the positions of the stars have shifted and perhaps eons have or rewound. The sensation would be akin to the ultimate crossing physical distance, but the very structure of reality. Such imagery can serve as a focal point for reflection on the transitory nature of existence, the fluid time, and the boundless potential that lies within the fabric of the universe. Imagine for a moment that you are drifting through the vast tapestry of the cosmos. Stars glimmer in every direction, their light scattered across an endless ocean of darkness. The silence of space is profound, yet somehow comforting, and you feel a deep sense of awe at the sheer magnitude of all that surrounds you. As you float weightless, you begin to sense a subtle distortion in the star field ahead. Something shifts in your peripheral vision, an area where space itself seems to bend, curving in upon itself as though forming a tunnel leading somewhere else. This phenomenon, known in theoretical physics as a wormhole, has captured the imagination of scientists, storytellers, and dreamers alike. For within such a cosmic corridor, so the theory goes, you might traverse not only enormous distances in space, but also, perhaps, leap across the boundaries of time. To appreciate how a wormhole might function, it helps to think of space-time, the combination of space and time, as a pliable fabric, capable of being shaped by the presence of mass, energy, and gravity. In Albert Einstein's theory of general relativity, space and time merge into this four-dimensional continuum, in which massive objects like stars and black holes carve deep curves, much as heavy marbles resting on a stretched rubber sheet create dips and valleys. The deeper the curve, the more strongly objects moving nearby will be pulled along. While this framework explains the familiar gravitational pull we experience daily on Earth, it also opens the door to more exotic possibilities, including the idea that space-time might fold in ways that link distant points or even different moments, creating tunnels, wormholes, through which a traveler might pass. Now, let your imagination craft a serene image of what this could mean on a cosmic scale. You drift through the darkness, guided only by starlight, and somewhere in the distance space ripples like the surface of a pond in the moonlight. You approach the distortion and peer inside. What appears to be a void or a tunnel might be the ivy mouth of a wormhole, a gateway that could lead you out the other side in some distant region of the universe, or perhaps even another epoch in time. If such an opening were stable and traversable, you might sail through in the blink of an eye, crossing what would otherwise require centuries or millennia of travel. It is a vision that inspires both wonder and caution, for wormholes, if they exist at all, are thought to be profoundly strange and potentially treacherous gateways. Though wormholes often appear in science fiction tales, they are not purely the stuff of fantasy. Certain solutions to Einstein's field equations, the mathematical underpinnings of general relativity, allow for the formation of these cosmic shortcuts. However, Just because the mathematics permits them doesn't guarantee their physical reality. Early on, scientists speculated that wormholes might be exceedingly small, popping in and out of existence at the quantum scale, far too fleeting to be noticed or used. Others have theorized that it might be possible for wormholes to form on a macroscopic level, or at least be enlarged artificially, if we had access to negative energy or exotic matter that could hold the wormhole's throat open. These ideas, while grounded in legitimate physics, remain highly speculative, yet they have attracted serious attention from renowned scientists, including the astrophysicist Kip Thorne, who explored how wormholes might be manipulated for travel across space and time, inspiring creative minds and filmmakers alike. In a more classical sense, think of folding a sheet of paper. If you label 2 points A and B on the paper's surface and fold the paper so that point A lies directly atop point B, then poking a hole through the paper effectively creates a shortcut between the 2 points. In a flat, two-dimensional surface, A and B would normally lie some distance apart, but with a fold they become adjacent. Wormholes extend that analogy into 4 dimensions, suggesting that large stretches of space, or even separate epochs, could be brought into close contact. The notion that these tunnels could serve as time machines arises when we consider how relativity merges time and space. Imagine a wormhole with 2 mouths, each positioned in a different frame of reference. Perhaps one mouth is placed near a massive object, such as a neutron star, where gravity is extremely intense, and the other mouth remains far away from such gravitational influence, or one mouth travels near the speed of light, while the other remains at rest relative to some observer. According to relativity, clocks run differently under strong gravitational fields or at high velocities. Time can slow down in these conditions compared to a region with weaker gravity or lower speeds. Thus, the 2 mouths of the wormhole may no longer be synchronized. You could enter one mouth and exit the other at a point in time that differs from the point you left, effectively enabling you to jump forward or backward relative to some outside observer. Yet for all its mesmerizing promise, the concept of wormhole travel raises formidable practical and theoretical challenges. First and foremost is stability. The equations that describe wormholes suggest they might collapse almost instantly upon formation, pinching off before anything can pass through. To counteract that collapse, exotic matter with negative energy density would be required to push back against gravity and keep the tunnel open. The problem is that such exotic matter, while theoretically proposed in certain quantum processes, has not been harnessed in a way that would allow large-scale engineering of spacetime. The energy requirements alone are staggering, beyond any technology we currently understand. It's as if you tried to lift an entire mountain range with just your bare hands. The scale of energy needed to maintain a stable wormhole is so vast that it has led many physicists to doubt that wormholes could ever become practical modes of travel. Even if the stability challenge were overcome, the possibility of time travel paradoxes looms. We might think back to the grandfather paradox and realize that a wormhole functioning as a time machine could create similar logical loops. If you emerged from a wormhole in the past, you might change events in ways that undermine your decision to travel back in time, creating contradictions. This puzzle suggests that if wormholes do permit time travel, reality might enforce certain restrictions on what travelers can do, or else time travel might prove impossible in ways we have yet to fully understand. Still, the human imagination is drawn to what wormholes represent, a potential liberation from the constraints of distance and chronology. Perhaps there is a universe in which cosmic civilizations have indeed harnessed such tunnels, forging shortcuts between star systems and weaving networks of commerce and knowledge across space and time. These ideas are reminiscent of the final frontier spirit in humanity's drive for exploration. Wormholes, in that sense, could be viewed as cosmic highways, bridging unimaginable gulfs and enabling us to see corners of the universe that remain inaccessible by any other means. Our comprehension of the universe expands and evolves, yet we remain creatures of finite perspective, reliant on instruments and theories that are constantly refined. There's a kind of peaceful acceptance in acknowledging that some of the universe's deepest secrets may lie beyond our current scope of knowledge. Wormholes like black holes, dark matter, or quantum phenomena remind us that reality can be more fantastic than we dare to dream, pressing us to keep asking questions, keep building telescopes, keep writing equations, and keep imagining possibilities. that challenge our intuition. Beyond the awe, there's also a meditative quality in contemplating these vast distances and the tunnels that might link them. Picture yourself inside such a wormhole, the walls of space-time curving around you like silken drapes, shimmering with the light of distant stars. You feel yourself moving, yet the journey is strangely calm, as if you're gliding along a gentle current. In an instant, assuming all goes well, you emerge into an entirely different region of the cosmos, where the positions of the stars have shifted and perhaps eons have passed or rewound. The sensation would be akin to the ultimate transformation, crossing not just physical distance, but the very structure of reality. Such imagery can serve as a focal point for reflection on the transitory nature of existence, the fluidity of time, and the boundless potential that lies within the fabric of the universe. But then come the sobering reflections on energy, stability, and the labyrinth of paradoxes. Kip Thorne and other pioneers in the study of wormholes often highlight just how extreme the requirements would be to maintain a traversable wormhole. Even if one naturally formed in the universe, channeling enough negative energy to keep it open long enough for macroscopic travelers to pass through could be the work of a civilization far beyond our technological horizon. The presence of strong tidal forces might also pose a significant threat, tearing apart any vessel or person that ventures too close to the throat of the wormhole. In many representations, wormholes share similarities with black holes in that both involve potent gravitational effects that could spaghettify matter. So while crossing a wormhole might be the height of cosmic adventure, it could also be an unfathomable risk. The potential for wormholes to facilitate time travel, specifically, often conjures the same swirling conundrums that we saw with the grandfather paradox. Could you use a wormhole to visit your younger self? Could you make changes that unravel the chain of events leading to your departure? Or is there some cosmic safeguard preventing such paradoxes from ever becoming reality? Some theoretical physicists propose the Novikov self-consistency principle, which suggests that any actions taken by a time traveler must already be consistent with history, meaning that if you do attempt to alter the past, your actions will somehow be integrated into the timeline that always existed. Alternatively, some interpret quantum mechanics to say that stepping through a wormhole into a different time might simply branch you off into an alternate universe, preserving the original timeline intact. Thus, you wouldn't so much change your past as create a new reality in which that change occurred. Whichever viewpoint one takes, the discussion serves as a reminder that time is not a simple, unalterable line. Instead, it might be a dimension as intricate and flexible as space itself, subject to warps, folds, and tunnels. And although we have yet to observe a wormhole directly, the tantalizing possibility they represent makes them a staple of both scientific inquiry and creative speculation. The synergy between theoretical physics and imaginative storytelling offers a perfect case study here. Mathematicians and physicists spin out possible geometries for space-time, while writers and filmmakers take those geometries and craft stories that capture the public's heart and mind. For the moment, let yourself dwell in the tranquility of this cosmic vision. You've sailed through the curved corridors of theory, glimpsed the potential for infinite shortcuts, and balanced on the edge of time itself. Each star you pass might be the home of countless mysteries. Each swirl of gravitational distortion could be the entrance to a new domain. The cosmic ocean is wide, and the wormholes, if they exist, might be hidden pearls in that dark expanse. As you take a slow, comforting breath, imagine reaching out to one of those pearls, feeling the gravitational tides tug at you, guiding you into an unfathomable beyond. And now, gently bring your awareness back to the present. Recognize that though our understanding of wormholes is incomplete, just pondering them can inspire an almost dreamlike sense of wonder. Such moments of contemplation remind us why we look to the stars in the first place, to expand our horizons, to question the limits of the possible, and to remain open to the awe of discovery. The essence of our curiosity about wormholes can be seen as part of a broader yearning to understand the cosmos and our place within it. In exploring these theoretical tunnels, we also explore our own capacity for hope, ambition, and creative thinking. This phenomenon is a consequence of traveling at high speeds or dwelling in strong gravitational fields, and though it might seem more modest than crossing a wormhole, it nevertheless has dramatic implications for how we experience and measure time. We will see that even without exotic space-time tunnels, moving at near light speed can warp our sense of duration and open a door, however narrow, to seeing the future in a way we never expected. How does this occur? Why does velocity or gravity distort time's flow? As we begin to explore these questions, let the calm curiosity within you linger, ready to embrace another facet of this grand cosmic puzzle. Picture the stretch of cosmic fabric bending and twisting in ways that defy your everyday intuition. Let your imagination float through these connecting passageways, even if only in a reverie, savoring the sense of wonder that arises whenever we contemplate phenomena so far beyond our ordinary experience. And with that sense of intrigue, look forward to discovering how traveling at extreme speeds can further illuminate the flexible nature of time, perhaps revealing that the gateway to the future doesn't require a tunnel at all, but merely the willingness and capability to venture into the domain where physics shows us that time flows differently. We have completed our sojourn through wormholes and are now ready to descend into the realm of time dilation. Allow yourself to sink into a gentle state of contemplation. Feel the rhythm of your breath and the subtle ebb and flow of your thoughts. Now, picture yourself standing on a quiet, open plain, gazing at the night sky. Above you, countless stars shimmer against the deep velvet backdrop of space. It is vast and seemingly unchanging, yet you sense a hidden dynamism, a dance of celestial bodies moving at unimaginable speeds. Within this cosmic ballet lies a phenomenon that redefines our understanding of time itself. We call this phenomenon time dilation, and it arises from the insights of Albert Einstein's special relativity. Though it may seem abstract at first, time dilation has a direct connection to the possibility of traveling into the future. Let us explore how movement, speed, and the very fabric of reality can warp our experience of time. When Einstein formulated his theory of special relativity in 1905, he challenged a deeply entrenched idea, the notion that time was absolute, passing at the same rate for everyone, everywhere. Classical physics assumed a universal clock ticking in perfect synchrony for all observers, but Einstein proposed something revolutionary. Time is not independent of our motions or our perspectives, but intertwined with space. As observers move relative to one another, their measurements of space and time shift accordingly. The faster you move, the more pronounced these shifts become. One key outcome is that a clock traveling at high velocity will tick more slowly compared to a clock at rest. This difference in the flow of time is time dilation, literally, the stretching of time experienced by a fast-moving traveler when compared to someone who remains stationary. It can be helpful to imagine two people. One remains on Earth, going about their daily routine, while the other embarks on a journey through space at speeds approaching that of light. According to special relativity, the traveling person's sense of time slows down relative to the person back home. If you could peer into the spaceship and watch the traveler's clock, it would appear to lag behind Earth's clock. Their seconds would tick by more slowly. Their hours would elongate. Meanwhile, from the traveler's perspective inside the spaceship, their own clock would feel perfectly normal, ticking at a regular pace. Upon returning to Earth, however, they might discover that far more time has elapsed for those who remained on the planet than for themselves. This discrepancy reveals time's pliable nature under extreme velocities. A classic illustration of this phenomenon is the so-called twin paradox, which, despite its name, is not a true paradox, but rather a vivid demonstration of how differently time can pass in distinct reference frames. Picture a set of twins born on Earth. One twin stays behind, living day by day in an ordinary way. The other twin boards a spacecraft and travels near the speed of light to a distant star, then returns, completing an interstellar round trip. While the traveling twin may experience only a few years of subjective time, the twin on Earth might grow old, experiencing decades. When the traveling twin finally comes home, they could be physically much younger than the sibling who never left. This scenario dramatizes just how radically high-speed travel can warp the flow of time. Although it may seem like science fiction, we already see measurable examples of time dilation in real-world experiments. Technological marvels such as GPS, satellites rely on highly precise clocks to provide accurate location data. Because these satellites orbit Earth at high speeds and also experience weaker gravity relative to clocks on the ground, they are subject to both special relativistic, velocity-based time dilation and general relativistic, gravity-based effects. Engineers must constantly correct for these time discrepancies. Though the differences amount to fractions of microseconds, they accumulate quickly and would render the GPS system useless if not compensated. In particle accelerators, subatomic particles traveling at velocities near the speed of light live significantly longer, in terms of their own internal decay timelines, than they would at lower speeds. These real-life confirmations, though minuscule, on human scales, validate Einstein's theory and remind us that time dilation is not just a mathematical curiosity, it is part of our day-to-day technological reality. For most of us moving at ordinary speeds, time dilation is negligible. The airliners we fly in, the cars we drive, and the trains we take barely graze a fraction of the speed of light, making their effects imperceptible in everyday life. Nevertheless, even a slight increase in speed can, in principle, shift the way time passes. Were you to circle the Earth on a supersonic jet for months on end, an ultra-sensitive clock would detect that slightly less time had passed for you compared to your friends on the ground. The difference might be a fraction of a second, but it is there, revealing the universe's underlying relativistic nature. Once we acknowledge these experiments and examples, we can begin to see time dilation as a small gateway to future time travel. While we often think of time travel as a dramatic leap into tomorrow in the blink of an eye, relativistic travel shows that by speeding up, you can effectively move forward in time relative to those who move slowly or remain still. If technology ever allows for near light-speed travel, an astronaut could, in principle, experience just a handful of years while centuries unfold back on Earth. In this sense, traveling into the future is not merely the stuff of fiction, it is a natural consequence of motion at relativistic speeds. But what would that feel like psychologically? Imagine climbing into a spacecraft, hearing the engines roar, feeling the surge of acceleration, and watching Earth vanish behind you as you approach velocities close to light itself. Aboard your vessel, days and nights might continue to cycle in some semblance of normality, depending on how you choose to organize your routine. Perhaps you keep a schedule for exercise, meals, and sleep, and so your internal sense of time remains relatively stable. Yet outside your window, stars blur into bright streams as you push forward through the darkness. Meanwhile, on Earth, entire generations could rise and fall, civilizations might evolve, and your friends and family could be long gone by the time you return. This dramatic shift in timelines is both exhilarating and sobering, an adventure into the future that transforms your personal connection to the familiar world you once knew. Although such extreme travel remains beyond our current capabilities, the incremental nature of time dilation at lower speeds is already in effect. Even if you simply climb into a plane and circle the planet, a more subtle version of this phenomenon unfolds. You and your seatmate experience time a tiny fraction of a second slower than if you stayed at home. Our technology allows us to measure this, but it's far too minute to notice on a human timescale. Yet the principle remains. The faster you go, the slower time flows for you, relative to those left behind. Speed becomes a kind of key, unlocking the door to temporal displacement. Reflecting on time dilation also invites us to consider the deeper relationship between space and time. Einstein showed us that these two aspects of reality do not stand alone. They weave together in a four-dimensional fabric called space-time, where motion in space always affects the passage of time. It's as though each of us carries a personal allotment of space-time, and as we move through space, we must spend some of our journey in the dimension of time differently than someone who remains still. This interplay can be both elegant and perplexing when we ponder traveling at velocities near the speed of light, where the differences become extreme and the boundary between present and future blurs. Philosophically, time dilation prompts intriguing questions about the nature of destiny and free will. If an astronaut leaps centuries ahead of a planet-bound humanity, does that future exist in some sense before they arrive? Or does their journey help bring that future into being? These questions merge with broader contemplations about time's flow, the arrow of causality, and our place in the cosmic timeline. Although Einstein's equations don't quite solve these riddles, they lay the groundwork for seeing time as malleable, revealing that our everyday understanding of past, present, and future is incomplete. For those who desire a more meditative approach, you might close your eyes and visualize what it would be like to embark on such a journey. Imagine drifting through space, far from Earth, your spacecraft gliding through a silent vacuum. Perhaps you watch the starfield shift, cosmic sights outside your window, gradually morphing as you press further into unknown regions. Inside, the days feel routine. You eat, sleep, read, and pass the time much as you might on Earth. Yet the knowledge that your clock is ticking more slowly instills an ethereal sense of detachment. Every moment you experience is stretched. When you eventually decide to return, you might be stepping into an Earth that has aged beyond your wildest dreams. Experiments confirming time dilation, such as those involving atomic clocks on aircraft, satellites, and spacecraft, have settled any lingering doubt that might have persisted after Einstein's bold conjectures. In every case, measurements show the traveling clock runs a bit slower compared to an identical one on Earth, precisely as predicted. These demonstrations, though they may involve tiny fractions of seconds, reaffirm the underlying principle that if we only had the means to travel faster, much faster, the effect would magnify dramatically. In that sense, time dilation is not just an abstract phenomenon locked in the equations of relativity, but a real, tested aspect of the universe. Now we arrive at an interesting juncture in our larger exploration of time travel. Wormholes, paradoxes, and cosmic conundrums can make the mind spin, but time dilation stands out as a comparatively straightforward glimpse of how we might move forward in time faster than our fellow inhabitants of Earth. The arrow of time for each person depends on their motion. If you rocket away at near light speed and come back, you will have effectively jumped forward. And yet, as established by the twin paradox example, the cost of such a journey might be emotional, existential, and deeply personal. You might find yourself in a future where familiar faces are gone, societies have changed, and you are an alien visitor in your own homeland. This tension underscores the emotional dimension of time travel that is often overshadowed by the scientific minutiae. Consider, again, the moment before takeoff. You stand on the launch pad, feeling anticipation and a certain weight in your chest. You look at the sky, and in your mind you imagine the path you will carve through space-time, each second elongated as your velocity increases. You also picture the time on Earth whizzing by in your absence. Perhaps you wonder about birthdays you will miss, the progress of human events, and whether you will even recognize the world upon your return. This reflective pause can be as important as the physical journey because it reminds you that time dilation touches upon fundamental human concerns: love, loss, relationships, legacy, even as it captivates us with cosmic grandeur. Now, let yourself rest for a moment, eyes closed or softly focused on a point in the distance. Envision soaring through the interstellar medium, your spacecraft a bubble of life and warmth against the void. Days pass for you in an orderly fashion. You mark them off on your calendar, read books, listen to music, communicate as much as you can with mission control. Meanwhile, decades or centuries might unfold back on Earth. Imagine the day you decide to turn around, burning your engines to reverse course and head home. With each passing hour, the sense of dislocation grows. You reflect that you might be returning not just to a changed Earth, but to an era beyond your own birth date. When you eventually descend through Earth's atmosphere, you land in a future that, from your perspective, has arrived in no time at all, and yet is so far removed from everything you once knew. This is not an abstract dream, but the logical outcome of traveling at high speeds in a universe where time is relative. With these reflections fresh in your mind, take a moment to let your breath slow. Close your eyes if you feel comfortable doing so. Perhaps you can hear the faint hum of engines that exist only in your imagination, transporting you beyond the bounds of the everyday. In that space of stillness, picture the seconds of your life as beads on a string. Each is precious and personal to you, even though someone moving differently through space-time might be collecting them at another rate. Picture how, if you traveled fast enough, that string of seconds would stretch, and by the time you let it slacken, you would be returning to a future that for you arrived quicker than expected, but for others unfolded in its natural course. We will explore the idea that reality might split or branch, offering alternate routes around the dead ends of paradoxes. Are these multiple timelines a theoretical convenience, or do they reflect something fundamental about how our universe operates? By wrestling with these concepts, we will further illuminate the labyrinthine possibilities that appear whenever we challenge the steadfast march of time. For now, rest in the knowledge that time dilation has already shown us a slice of these marvels in a form that can be tested and observed. We can begin by recalling the threads that led us here. Over the course of our journey, we have considered time travel paradoxes like the grandfather paradox, the possibility of traversing space-time through wormholes, and the phenomenon of time dilation, as described by special relativity. Each of these ideas highlights a potential twist in the fabric of time, a scenario that challenges the linear, forward-only narrative we typically accept. But these twists and contradictions can be unsettling, making us wonder if something is fundamentally wrong with the notion of traveling back or forward in time. The multiverse theory offers one possible resolution by suggesting that reality can branch into different universes, each with its own version of events. In its broadest form, the multiverse theory posits that there is not a single unique universe, but rather an endless collection of them. Within this collection, every possible outcome of every event takes place somewhere and somehow. Imagine flipping a coin. In our usual view, that coin must land heads or tails in your single reality. The other outcome simply does not happen. But from a multiverse perspective, both outcomes occur, heads in one branch, tails in another, leading to two distinct universes that proceed independently. This idea gains traction in certain interpretations of quantum mechanics, most famously, the many worlds interpretation proposed by physicist Hugh Everett III in the 1950s. According to many worlds, quantum events do not have a single outcome. Rather, they spread out across multiple parallel realities, each outcome just as real as the other. At first glance, this notion can seem perplexing, some might say extravagant, because it suggests an unfathomable proliferation of universes. Yet from a mathematical standpoint, the many worlds interpretation can elegantly address certain paradoxes in quantum mechanics without requiring special mechanisms such as wave function collapse. The trade-off is accepting that the reality you experience is only one among countless possibilities. If you follow that logic, then each time you make a choice, turn left or turn right, you branch into different timelines. In one universe, you took the left turn, in another, the right turn. Thus, the sense of a single continuous story might be an artifact of your consciousness, tracing a particular path through this vast branching structure. How, then, does this idea relate to time travel? Consider the grandfather paradox once more. You travel back in time with the intent of preventing your grandparents from meeting, thus erasing your own lineage. In a single universe model, this creates a paradox, for if you succeed, you cannot exist in the future to make the journey, contradicting your presence. But if multiple timelines exist, your attempt to alter the past might not rewrite your original timeline at all. Instead, it could generate or shift you into a different timeline, one in which your grandparents never met, and thus you were never born, at least not that version of you. Your original timeline remains intact. The act of traveling back simply deposits you into a new branch, separate from the one that led to your birth. In this way, the paradox dissolves, replaced by a scenario of multiple outcomes, all equally real but unfolding in separate streams of events. This explanation can alleviate logical conflicts, but it raises new questions about identity and continuity. If you shift into a different timeline, are you still you, or have you become something else entirely, a guest in a universe that wasn't originally yours? Some speculative thinkers suggest that traveling between timelines might be akin to stepping through a doorway into another dimension, bringing your personal consciousness with you. The inhabitants of the new timeline, meanwhile, may recognize you as a stranger, or they may never notice if you choose to remain hidden. Each detail depends on how thoroughly you alter events and how you interact with your alternate reality. From a meditative standpoint, contemplating the multiverse can be both humbling and freeing. There is a sense of limitlessness. Every decision you did or did not make, every outcome that could or could not happen, unfolds somewhere within an unbounded expanse of realities. One might view it as an infinite cosmic tapestry, each thread representing a universe, each weave intersecting with countless others. If you choose to step back and regard this tapestry from a serene distance, you see that no single thread stands alone. All are woven together in a multidimensional pattern, each with its own past, present, and future. Time, within this vast perspective, becomes a local phenomenon, a line that extends within a given universe, while the grander structure extends across a myriad of parallel lines. Some proponents of the multiverse theory believe it can explain more than just time travel paradoxes. They look to cosmic puzzles, such as why the physical constants of our universe are so fine-tuned for life, and suggest that we simply happen to exist in one branch that supports our kind of chemistry and biology. Other branches might have different constants that render them barren or unstable. In that sense, the multiverse offers a framework in which the improbable becomes inevitable. If there are infinite rolls of the cosmic dice, one outcome that fosters life and consciousness is bound to occur somewhere. While these speculations may or may not be directly tied to time travel, they reveal the breadth of thinking the multiverse invites. Yet, with such speculation comes the challenge of empirical verification. How do you prove or disprove the existence of other universes that branch away from your own? A widely recognized difficulty is that by definition these other universes are inaccessible, except perhaps through extraordinary means, wormholes, advanced quantum manipulations, or hypothetical constructs we can scarcely imagine. Some physicists argue that while the multiverse theory might be philosophically appealing or mathematically consistent, it strays beyond the current limits of testable science. Others maintain that certain cosmological observations, like the cosmic microwave background, could yield indirect evidence of collisions or interactions with other universes, though such interpretations remain contentious and far from settled. 2. Truly feel the multiverse on a deeper level. Imagine yourself in a quiet room, perhaps sitting cross-legged or in a comfortable chair, eyes half closed. Take a few slow breaths and visualize your life path. Childhood, adolescence, the many twists and turns that have led you to this very moment. Each memory glows faintly in your mind like stepping stones behind you. Now, imagine these stepping stones branching off from each point of decision, each chance encounter, each moment of triumph or loss. Every what-if you have ever pondered extends into its own luminous path. Some lead to joyful possibilities, others to sorrowful outcomes, and still others to destinies that are neither clearly good nor bad, but different in subtle ways. This is, in microcosm, the idea of many worlds. You occupy one of those paths, but somewhere out beyond your immediate reach, every alternate choice thrives as its own reality. In that state of reverie, you might discover a surprising comfort. In the multiverse notion, perhaps the regrets you harbor, the road not taken, the words not spoken, unfold somewhere shaped into their own entire universe. Or maybe the greatest hopes you have for yourself or humanity are realized in a parallel timeline, even if not in yours. One might say that all possibilities are validated, that nothing is entirely lost or left unrealized. But on the flip side, acknowledging this multiplicity of possibilities can leave one grappling with existential questions. If everything that can happen does happen, then what do our choices truly mean for our personal identity? Are we free to craft our own story, or are we just one version among a cosmic library of versions? The multiverse theory, in this sense, fosters a blend of wonder, self-inquiry, and philosophical unease. Now, from a more scientific vantage point, multiple timelines can manifest in ways other than the many worlds interpretation. For example, some theories in cosmology posit a grand inflationary multiverse, in which eternal inflation spawns bubble universes endlessly, each with its own physical laws. Others suggest a branching structure to time itself, akin to a fractal that grows at each quantum measurement. Still others propose that parallel universes might exist in higher dimensional space, stacked or layered in ways we cannot perceive with our limited senses. While these variations differ in their details, they converge on the idea that our reality is not singular. This environment of theoretical creativity speaks to humanity's boundless fascination with time, existence, and the ultimate scope of what is real. As we refocus on time travel specifically, the multiverse can offer a resolution to paradoxes that might otherwise seem unsolvable in a single timeline universe. But it also transforms how we conceptualize what travel means. Instead of rewriting the past or forging a path to the future of your native timeline, you might be stepping into another reality altogether. If so, does it count as traveling through your own time, or simply jumping across the boundaries between universes? And if you do this, are you forging new connections among these parallel worlds, or are you merely observing them as a ghost in a story that was never meant to be yours? In many speculative works, this is where the concept of moral or narrative responsibility arises. If you find yourself in a timeline that is not your own, how should you behave toward the people and events unfolding there? Do you have the right to intervene to shape that reality's future, knowing it isn't the one you came from? Such dilemmas echo the broader ethical concerns of meddling with time itself, layered with an additional complexity. Now you are not only shifting events in your own history, but possibly impacting countless other histories as well. Ultimately, the multiverse theory is less a single, polished explanation than a broad family of ideas, each wrestling with the fundamental question: are we alone on our timeline, or does reality include innumerable other timelines? Like any profound concept, it sits at the intersection of science, philosophy, and imagination. Hard evidence for these ideas remains elusive, and it may stay that way for some time, if not forever. Yet, the imaginative leap toward multiple realities opens doors to new ways of understanding existence, of addressing paradoxes, and of pondering our place in the cosmic scheme. At this juncture, you might once again close your eyes or soften your gaze and take a gentle breath. Picture the entire multiverse as a shimmering tree with infinite branches. Each branch represents a universe, and each leaf on that branch represents a moment in time within that universe. The leaves flutter in some cosmic breeze of possibility, shimmering in the faint glow of potential. That tree stands as an emblem of creative plurality, reminding us that the story we call our life could be one among countless narratives, all equally vivid, all equally valid. In some branches you found success early, in others you took a different path, in still others history itself diverged, shaping worlds of unimaginable difference from ours. From here, our exploration of time travel continues into realms where these theoretical constructs meet the imagination, fueling further speculation and storytelling. The idea of multiple timelines can meld with time dilation, wormholes, and paradoxes, painting an ever richer portrait of how reality might handle or circumvent the challenges of traveling through time. As you carry this new perspective forward, reflect on how the multiverse theory, in its various forms, stands as a testament to humanity's curiosity. Our minds stretch and strain to account for every puzzle that arises when we push the boundaries of our knowledge of space and time. We question whether the simplest interpretation, one universe, one timeline, is incomplete, and if so, how far we must go to capture the fullness of what could exist. Let this sense of curiosity remain with you as we near the close of this segment. The multiverse may never be fully proven or disproven, yet the very fact that we can conceive of multiple timelines, each forging its own path through the labyrinth of possibilities, may open us to deeper insights about our own choices, regrets, and hopes. From an emotional perspective, the concept of a branching reality can console us with the thought that somewhere, in some other dimension, things went differently, perhaps even for the better. Or it can challenge us to see that our actions in this reality matter profoundly, because we are the ones who bring them to fruition in our chosen branch. In concluding, let us rest in that meditative hush once more. Breathe in and envision the multiverse as a grand cosmic stage, with innumerable acts playing out simultaneously. Breathe out and gently return to the present moment, aware that at least for now, you exist in a single, continuous thread of reality. The concept of multiple universes remains a graceful hypothesis, shimmering in the background of our scientific and philosophical discussions. Whether or not it holds the key to time travel or solves its paradoxes will continue to be debated for years to come. Yet for those who dream of visiting the past without destroying the present, or glimpsing the future without losing what we cherish, the multiverse theory offers a window into a realm of infinite potential, daring us to gaze beyond the horizon of conventional thought. Begin by conjuring a scene in which you drop a pebble into a still pond. We're accustomed to seeing ripples spread outward after the pebble hits the water. Now, imagine the ripples reaching the shore before the pebble has even touched the surface. That sense of disorientation, of time turned upside down, captures the essence of retrocausality. It's not merely a flight of fancy. Certain interpretations of physics and quantum mechanics have hinted that signals might, under specific conditions, appear to travel backward in time, or at least behave in ways that are equivalent to such. Backward travel when examined from certain frames of reference. In daily life, we rely on a strict ordering of cause and effect. If we leave a glass perched on the edge of a table, it might fall and shatter, never the other way around. That arrow of time, leading from cause to consequence, provides a foundation for our understanding of how the world works. Yet the deeper we probe into the laws of nature, the more we notice that these laws, particularly in the realm of fundamental physics, do not always distinguish clearly between forward and backward directions of time. Many basic equations in quantum mechanics, electromagnetism, and other fields are time-symmetric. If you reverse the direction of time in the equations, you often get valid solutions that look mathematically consistent, though physically counterintuitive. This time symmetry in many physical laws prompts a question. If the laws themselves don't inherently forbid it, might it be possible for a future event to exert an influence on what has already happened? And if so, how would we notice such a phenomenon? Over the years, physicists have proposed various thought experiments to illuminate these questions. Some revolve around the idea of advanced waves, hypothetical signals that travel backward in time. Others draw on the peculiarities of quantum entanglement, where the outcomes of measurements appear to be correlated in ways that defy classical explanations. Still more revolve around delayed choice experiments proposed by the physicist John Wheeler, where the decision about how to measure a particle seems, in some interpretations, to affect the particle's past behavior. One illustrative scenario is the delayed choice quantum eraser experiment, a variation of the famous double-slit setup. Typically, if you shoot photons at a barrier with two slits, you might see an interference pattern on a screen behind the barrier, evidence that each photon behaved like a wave, going through both slits simultaneously. But if you measure which slit the photon went through, the interference pattern disappears. The quantum eraser twist occurs when you choose whether or not to erase that which path information after the photon has passed through the slits. So, in a sense, you're deciding retroactively whether the interference pattern should exist. While there is debate about whether this truly demonstrates a retroactive effect, it's a stark example of how quantum experiments can blur the standard sequence of cause and effect. Observations made in the present can appear to rewrite events that we would ordinarily think of as fixed in the past. Such experiments suggest that our everyday view of time as a simple forward-moving current might be too restrictive. Retrocausality. Here's one possible explanation for these oddities, positing that there could be genuine backward-in-time influences. Another viewpoint is that the universe only reveals information in ways that obey conventional cause and effect, but the underlying quantum reality is far less constrained. Whichever stance one takes, it's clear that quantum physics challenges the intuitive flow from past to future. Entangled particles, for instance, remain correlated in a way that appears instantaneous across distances, sidestepping the usual constraints of local causality. Some might speculate that part of this correlation emerges through connections that transcend time itself. If we take retrocausality seriously, then the implications are profound. We might envision scenarios where signals from the future nudge the present, shaping events in subtle ways so that we unknowingly fulfill a destiny already laid out by future conditions. This notion ripples outward to challenge philosophical concepts of free will and determinism. If the future can impact the past, how do we define our sense of choice in the present? Are we truly free, or are we simply enacting outcomes that exist in a loop, fixed by constraints flowing from both directions in time? Some researchers explore these possibilities by focusing on the deep structure of quantum mechanics, searching for hidden variables or alternate formulations that could incorporate retrocausality naturally. Others prefer simpler interpretations that maintain the usual arrow of time, at least for practical purposes. Still, the thought remains, if time is symmetrical at its core, then perhaps cause and effect need not always align with our experience of forward progression. This opens the door to time loops, in which a future event is not just predicted by a past event, but also helps bring that past event into being. Science fiction often leverages such loops for dramatic effect, but they arise from genuine questions about how quantum processes unfold and how measurement ties to outcomes in ways that confound classical reasoning. Naturally, embracing retrocausality does not come without difficulties. If the future can influence the past, do we risk paradoxes similar to the grandfather paradox, where an action undoes its own cause? In the realm of quantum mechanics, certain paradoxes might be dampened by probabilistic outcomes that remain internally consistent while still allowing for backward-in-time correlations. The question is whether large-scale macroscopic events could ever exhibit retrocausal influence, or whether it remains confined to subtle microscopic phenomena. Thus far, the latter seems more likely. If retrocausality plays a role, it likely does so in the quantum arena, where the strangeness of entangled states and measurement can subvert classical expectations. Imagine, for instance, a particle traveling on a trajectory that splits, then recombines, an event that seems to be determined by your choice of how to measure it in the future. From a purely classical vantage, this is impossible. Yet mathematically, it might be interpreted as the future measurement informing the particle's behavior retroactively. Another way of viewing it is that the universe is a single coherent entity where the notion of temporal sequence is an emergent property. Past, present, and future could be deeply entangled within the fabric of space-time, and what appears to be retrocausality might be a reflection of a deeper, timeless structure. Some physicists speculate that at the root of reality, time itself could be an illusion, an emergent phenomenon from an underlying quantum geometry. Reflecting on retrocausality can lead to a sense of wonder and disorientation. In day-to-day life, cause precedes effect. This is as fundamental to our worldview as breathing. Yet these mysteries at the fringes of physics suggest a more nuanced reality. Rather than dismissing them out of hand, researchers continue to test the edges of quantum theory, looking for loopholes or consistent models that would allow backward-in-time signals, at least in principle. If conclusive evidence were to be found, it would rewrite our sense of chronology. But even if retrocausality remains a theoretical concept, it opens creative avenues for thinking about time, knowledge, and the interplay between observation and physical phenomena. It's crucial to note that retrocausality, in many interpretations, doesn't necessarily allow us to send readable information into the past in a way that leads to overt contradictions. Even if advanced signals exist, the quantum rules might ensure that no paradoxical messages can be deciphered, preserving the overall consistency of events we observe. In other words, there could be constraints that allow subtle, backward influences, without letting you kill your own grandfather or rewrite world history in blatant ways. This hints at a universe that is more flexible than we realize, but still maintains an overarching coherence. Quantum entanglement is often brought up in these discussions because it exemplifies correlations that seem to transcend space-time limitations. Two particles created in an entangled state behave as if they share information instantly, no matter how far apart they drift. One interpretation is that measurement outcomes become defined only at the moment of observation, and that there is no signal traveling between them. Another suggests that hidden variables exist outside conventional space-time constraints. A more radical approach is to propose that some aspect of the measurement is influenced by future boundary conditions, effectively sending signals backward in time. Whichever stance one takes, entanglement shows that quantum events can subvert classical cause and effect assumptions, giving credence, if only tangentially, to the notion that time might not be as one-directional as we perceive. Gently returning to the pebble and the pond analogy, you might consider that perhaps the ripples aren't truly appearing before the pebble lands, but the pond contains a subtle network of waves that can converge and interfere in a pattern that only makes sense once the pebble hits the surface. The effect might look reversed if you film it and interpret it in a certain way, but in reality, it's part of a more holistic interplay. Retrocausality arguments often rest on similar logic. Maybe there's no actual backward signal, but the overall system is arranged so that past and future events coordinate in ways that appear to defy the arrow of time. Seen in this light, retrocausality can be less about rewriting history and more about revealing that the entire timeline is shaped by conditions spread across past, present, and future, all woven together in the tapestry of space-time. From here, we come to a natural question. If retrocausality is possible, how do we avoid the logical pitfalls of paradox? The moment we allow the future to shape the past, we run the risk of contradictory loops, threatening coherence in our timeline. This leads us directly into a concept known as the Novikov self-consistency principle, which states that any event capable of influencing the past must do so in a way that does not generate inconsistency. In other words, even if time can curve back on itself, the universe finds a path that preserves logical consistency, preventing paradoxical outcomes. One might imagine that if you tried to use retrocausality to alter a historical event, your attempts would either fail or somehow become the reason that event happened as it did. This principle effectively says that while retrocausality might exist, the universe protects the integrity of cause and effect by ensuring that all actions fit neatly within a coherent timeline. In the next segment, we will delve more deeply into the Novikov self-consistency principle, examining how it provides a framework in which retrocausality and other time travel scenarios could potentially occur without tearing holes in logic. For now, allow yourself to rest in the feeling of curiosity that arises from contemplating signals that might, in some sense, run backward in time. Notice how the mind struggles to reconcile this with the everyday chain of causes and consequences. Feel the gentle tension in your thoughts, an intriguing reminder that the reality we take for granted may only be a fraction of what truly exists. Let your next inhale be slow and deliberate, and imagine energy moving from some future moment into this present breath, as though time were more fluid than we normally assume. On the exhale, let the idea dissipate gently, leaving a soft imprint on your consciousness. The enigma of retrocausality isn't easily resolved. It taps into the bedrock of physics, questioning how quantum events might interweave with space-time's structure. Whether or not we ever definitively prove signals from the future can shape the past, the concept stands as a testament to the boundless creativity of our quest to understand time's mysteries. It reminds us that cause and effect, so reliable in our daily lives, can become more subtle and intricate when we explore the quantum depths. As we part from this exploration, keep the door to possibility slightly ajar. Retrocausality may turn out to be a helpful metaphor rather than a literal fact, or it might be a signpost pointing to revolutions in our understanding of physics yet to come. With each new development in quantum theory and experimental investigation, we chip away at the veneer of certainty that time moves one way and one way only. We may find in the end that time is more akin to a tapestry woven from past, present, and future threads, each supporting and defining the others in ways that defy a simple linear narrative. Thus, we step closer to understanding how the future might indeed fold into the past, and how the universe might protect its own coherence even when cause and effect begin to blur. Take one more moment to sit quietly, letting retrocausality ripple in your thoughts like a faint echo of a future wave that has yet to crash onto the shores of the present. Then, when you're ready, turn the page to discover how self-consistency might save us from the loops that otherwise threaten to unravel the tapestry of time. Allow yourself a few slow, deliberate breaths. Let your thoughts drift back to all the paradoxes and puzzles we've uncovered about time travel, moments where events appear to contradict themselves, where traveling backward in time threatens to unravel the very cause that allowed the journey in the first place. Now imagine a profound yet calming resolution to these contradictions. In the early 1980s, physicist Igor Dmitrievich Novikov proposed an idea called the Novikov self-consistency principle, a framework suggesting that time travel may be possible, but only in ways that preserve a single, consistent history. According to this principle, any action you take, even if you travel back in time, was always part of history's tapestry. No matter how counterintuitive it sounds, you cannot break causality because your actions, however surprising, were always woven into the timeline. To illustrate this principle with an example, picture yourself discovering a time machine in your present. Perhaps you've always harbored a regret about an event from a decade ago, a career choice, a slip of the tongue, or even a personal tragedy that shaped your life. With trembling excitement, you step into the machine, intending to rewrite that piece of history. But as the Novikov self-consistency principle emphasizes, events cannot be fundamentally changed because the past is fixed in the sense that it already accounts for whatever you, the time traveler, are about to do. If you attempt to prevent the event, something will arise. Coincidence, an unforeseen mishap, or your own subconscious hesitation that ensures the event still transpires. The principle says you will find that your well-meaning interference is paradoxically the cause that makes the event unfold in the way you remember. In other words, suppose you want to stop a friend from being in a specific accident that shaped your life's course. You arrive at the scene at the critical moment, only to realize that your sudden presence distracts a passerby who might otherwise have intervened, causing the accident to occur exactly as it did in your memory. In the process, you learn that your attempt was already baked into the timeline. Your efforts weren't meaningless, but they were precisely the ingredient that ensured history remained intact, preserving the consistency of events. Within Novikov's framework, the past is not open to revision. Instead, when time travelers venture back, they fulfill the role they always had, whether they knew it or not. Such an idea can feel counter to our usual notion of agency. We often think of free will as the ability to choose from multiple distinct possibilities. If the future is malleable, then so too should be the past, right? But under Novikov's principle, the past is set in stone because we have already observed its outcomes. If one day we perfect time travel, those journeys back in time will simply materialize within events that have, from our present vantage, already transpired. Instead of changing the past, you become an unseen actor within it, fulfilling something that was always fated to happen. This line of reasoning challenges our sense of autonomy. Are we truly free if all attempts to alter the past are doomed to become the seeds of that very past? The principle suggests that either free will is an illusion, or it is so constrained by the dictates of space-time that all your choices align with outcomes that maintain consistency. Paradoxically, you might feel yourself making decisions of your own accord, yet those decisions fall in line with what has been historically recorded. The puzzle of free will has long been debated in philosophy, but the Novikov self-consistency principle adds a fresh twist to it. Even if you have subjective freedom, the objective shape of history might not budge. Before diving more deeply into these implications, consider how elegant this principle can be in resolving paradoxes. Time travel stories often hinge on the possibility of preventing one's own birth, as in the grandfather paradox, or altering the course of history in catastrophic ways. Yet, according to Novikov, no matter how hard you try to meddle with crucial past events, consistency will be preserved. You might set out to assassinate your grandfather, only to discover that every bullet mysteriously misses, or you lose your nerve at the last second, or your grandfather wasn't truly your biological relative. Some unanticipated turn of events bars you from violating the chain of causation that leads to your existence. The net result is a world without contradictions, one in which all attempts at rewriting history morph into the exact actions that cement history's already known outcome. If you exist in the present, you must have failed to erase your lineage in the past, although you might have unwittingly shaped it in a way that was always meant to occur. This sense of inevitability can feel both comforting and stifling. It's comforting insofar as it insulates reality from destructive paradoxes. The laws of physics maintain a logical continuity, preventing the universe from collapsing into contradictory states. It's stifling because it implies that traveling back in time holds little capacity for genuine change. The principle suggests that you can observe, you can participate, but you cannot truly alter pivotal events. If, for instance, you traveled to watch the building of the pyramids or to witness the Renaissance unfolding, you would be there only as part of the tapestry that already includes your presence, invisible or overlooked in the history books. You might hand a tool to a worker or pass along some information, but these actions would have been accounted for all along, woven invisibly into the narratives we already know. To conceptualize this in a simpler way, imagine writing a diary entry about a normal day in your life. Unbeknownst to you, the day's events included the presence of a stranger who intervened at a critical moment. You might not realize the significance of that intervention or even notice the stranger at all, but you record the outcome in your diary, perhaps an outcome that shapes your future in a profound way. Later, if you become that time traveler, you step back into that day playing the role of the stranger. By participating in these events, you ensure that they happen just as recorded. Through this lens, time travel is not so much rewriting history as it is filling in invisible details of the existing record. You played both the cause and the effect, a loop that never strays from the single, consistent timeline. Quantum physics offers an intriguing parallel to Novikov's principle. Although quantum mechanics typically deals with probabilities rather than certainties, certain interpretations suggest that all events that occur must remain consistent across potential timelines. Quantum entanglement shows us how strongly correlated different parts of a system can be, as if the universe demands an internal harmony that defies simple classical explanation. Novikov's principle, though more of a classical concept than a quantum one, resonates with that sense of cosmic self-consistency. Things happen in ways that maintain coherence, no matter how counterintuitive they might appear. Critics of the Novikov self-consistency principle argue that it may simply restate the obvious. We do not observe paradoxes in reality, so presumably nature forbids them. Yet does that truly prove that time travel to the past is possible? Others note that the principle is less a physical law than a condition, an assertion that if time travel is possible, it must be subject to the constraint of consistency. For many researchers, the existence of closed time-like curves, paths through space-time that loop back on themselves, remains a theoretical possibility in solutions to Einstein's field equations of general relativity, but the practical feasibility and stability of such curves are still open to debate. Novikov's principle thus stands as a conceptual guardrail, a rule preventing these curves from generating logical impossibilities. In the realm of the imagination, stories abound where travelers discover they cannot change the past because they were always part of it. In some tales, an individual's attempt to halt a disaster only triggers a sequence of events that causes it to happen. In others, a time traveler striving to warn historical figures of impending doom is dismissed or thwarted, ensuring history remains unchanged. Such narrative twists align closely with Novikov's stance. No matter the traveler's intent, everything they do becomes exactly what they did all along. The emotional arc of these stories often revolves around the traveler's slow realization that they are not rewriting history but fulfilling it. The principle can instill a sense of cosmic irony, a notion that fate is more powerful than free will, and that destiny remains unyielding against even the mightiest interventions. It's worth stepping back to appreciate the tension between Novikov's principle and our sense of autonomy. If you had the power to step back into a moment from your own childhood, you might assume you could make a different choice, give your younger self new advice, or redirect a painful outcome. According to self-consistency, however, any attempt to alter that timeline would either fail or would become the very cause of the outcome you remember. It may be that your presence in that childhood scene was always a hidden part of the story. This realization can lead to a sobering perspective. Are we all just characters in a cosmic narrative that has only one fixed script? Or can we still claim to be authors of our own destinies, choosing our path in the present while the past remains immune to alteration? To explore such questions, reflect on the difference between theoretical possibility and practical experience. In practice, we do not currently have a confirmed method for traveling backward in time, so these debates remain speculative. One could argue that if backward time travel were truly feasible, we would see evidence of historical anomalies, people or artifacts misplaced in time, and yet, to our knowledge, we do not. Perhaps that is because time travel never occurs, or perhaps it is because time travelers strive to remain inconspicuous to avoid paradoxes, or because their presence was always integrated in the timeline from the start, unnoticed or misunderstood. In historical records, any of these interpretations can be consistent with Novikov's principle. The principle simply states that if these travelers exist, they will not generate paradoxes, and thus they could exist without our explicit awareness. A philosophical sense, the Novikov self-consistency principle can merge with certain determinist viewpoints. If all events are determined, then of course any hypothetical time travel must align with that determination. If you are meant to exist in the present, your journey into the past cannot erase your birth. But for those who believe in a more open future, the principle might cause discomfort. It implies that at least some portion of the timeline, everything behind you, is unalterable, and that attempts to reshape it from the vantage point of the future are already constrained. This constraint bleeds into the notion of free will regarding the past, while leaving the future's openness more ambiguous. Is the future equally fixed, or does free will only apply to events that have not yet been observed? Novikov's principle does not directly answer these broader existential concerns, but it does cast them into sharper relief, demonstrating how tricky time travel scenarios can become when pressed to their logical limits. Take a moment to let these reflections settle. Inhale deeply, feeling the calm in your body, and imagine yourself as both the cause and effect of events that must happen. The sense of inevitability might be soothing in one way. It means you are a seamless part of the universe's grand design. On the other hand, it may be unsettling to consider that your attempts to alter the past could be predestined to fail, that every choice you make is circumscribed by a tapestry woven through all time. Yet this is precisely the paradox-resolving power of Novikov's principle. It keeps the universe logically intact, ensuring that contradictory loops in time cannot form. From here, let us prepare to explore what happens when we examine those loops more closely. The next segment will delve into causality loops themselves, those closed chains of cause and effect that sometimes show up in discussions of time travel. We've touched on the notion that travelers can become part of an event's own history, but we will now wander deeper into scenarios where the past and future feed into each other continuously. What if an item or a piece of information is its own origin, existing only because it is passed from the future to the past? Such loops challenge our conventional sense of a linear timeline, and yet, guided by Novikov's principle, they remain coherent within a self-consistent narrative. As you transition to that next stage of exploration, keep in mind the core insight. From Novikov, no matter how perplexing a loop might be, it cannot violate causality in a way that undermines the existence of the loop itself. This idea invites us to imagine that the universe is capable of weaving extremely elaborate plots, so long as they resolve into a single consistent thread. And in those labyrinthine stories, we, the participants, may discover that our sense of autonomy is intricately bound up with the shape of the timeline. Whether we perceive that as a comforting or constricting truth is a matter for personal reflection. You awaken one morning to find a letter that appears to have been slipped under your door in the dead of night. The message addressed to you is unquestionably in your own handwriting, yet it bears a date from many years into the future. You read it with shaking hands, marveling at the intimate knowledge of your life's secrets that only you could possess. The letter urges you to take certain actions, promising that, in due time, you will understand its importance. As your life unfolds, you eventually reach the point when, holding the original in hand, you decide it's time to complete the cycle. You copy the contents word for word, seal them in an envelope, and deliver them to your younger self. The paradox stares you in the face. Where in all of this did the information in that letter truly originate? This scenario encapsulates the essence of a causality loop, sometimes called a bootstrap paradox. It is a curious phenomenon in which an event serves as the cause of another event, which in turn is among the causes of the first event. While it may sound like a convoluted idea concocted by science fiction writers, causality loops emerge naturally whenever one entertains the possibility of time travel or retrocausal effects. The hallmark of these loops is their circular structure. An object, person, or piece of information journeys through time only to become its own reason for existence. You might receive a message from your future self that compels you to perform certain actions, culminating in your choosing to send that message back once you reach the future. The loop is sealed. The message arrives because it is sent, and it is sent because it arrived. In science fiction, such loops are endlessly captivating. One famous example can be found in certain episodes of Doctor Who, where a character receives critical information from a future version of themselves, then proceeds to pass it along in the past, making it seem as though the knowledge simply materialized. Another instance, Robert A. Heinlein's short story By His Bootstraps revolves around a character who interacts with future and past versions of himself in such a way that he ends up creating his own origins. These stories highlight the beguiling appeal of the causality loop, something about an object or piece of knowledge that never appears to have a clear point of creation underscores a profound challenge to our normal understanding of cause and effect. To grasp why these loops are so puzzling, let us revisit the bedrock principle that events typically have a linear flow. Ordinarily, a cause precedes its effect. You plant a seed and later a plant grows. With causality loops, however, cause and effect intertwine to the point that the effect becomes its own cause. It's rather like the question, which came first, the chicken or the egg, but with an added dimension of time travel. The message, object, or person that traverses the time stream lacks a traditional origin. It exists in a closed cycle of time. We can trace its chronology forward or backward, but never discover the root event that created it in the first place. Did it spring from nowhere, conjured by the mere potential of time travel? This question leads to an unsettling realization. The loop seems to produce something from nothing. If the letter you received was composed of information that had never been learned or developed by anyone outside the loop, facts that do not derive from the normal progression of history, where did that knowledge come from? Does it constitute a violation of conservation laws, in the sense that new information or matter is popping into existence uncaused? Physicists and philosophers who ponder such loops often wrestle with the idea of whether they defy fundamental principles like conservation of mass energy, or whether time travel might allow for a rearrangement of existing matter and information in a way that is consistent but deeply paradoxical to the human mind. From a storytelling perspective, causality loops are thrilling because they embody a kind of cosmic riddle. If you are both the cause and the effect of something, can you even speak of a beginning? The storyline might revolve around a piece of futuristic technology that appears in the past, enabling leaps in scientific progress that eventually lead to the invention of that very technology in the future. The device effectively creates itself. Or perhaps a composer learns a piece of music when visited by an older version of themselves, then takes that knowledge forward until one day they pass it back to their younger self. The melody circles through time, never being composed in the usual sense, only discovered and rediscovered along an eternal loop. These narratives can be simultaneously awe-inspiring and profoundly disturbing to our linear mindset. In the context of theoretical physics, the idea of a causality loop often dovetails with discussions of closed time-like curves. These are paths in the geometry of space-time derived from Einstein's general relativity, which loop back to their point of origin. If such curves exist and if they can be traversed by information or physical objects, they enable time travel to the past. The presence of closed time-like curves raises the possibility of an event influencing itself, thus creating the conditions for a causality loop. Igor Novikov's self-consistency principle, which we explored previously, addresses the paradoxical scenarios this might generate, insisting that any sequence of events occurring along these loops must be consistent with the past as observed. In a sense, if a causality loop is to exist, it must do so in a way that avoids self-contradiction. Nevertheless, it still leaves the disquieting question of how something can appear to lack a definable point of origin or creation. Philosophically, causality loops challenge our notions of linear existence. We typically live with an unspoken assumption that everything has a beginning, a cause that sets it in motion. But if you receive that mysterious letter from the future, follow its instructions, and eventually send it back in time verbatim, you confront a logic-bending scenario. The letter is not authored in a single linear moment of creation. Instead, it emerges fully formed from the loop. Our classical understanding of time rests on cause preceding effect, but a loop implies that cause and effect are locked together in an eternal dance, each shaping the other. It forces us to question whether linear time is the only possible structure of reality, or if loops might exist in ways that are mathematically coherent, if not entirely intuitive. In some interpretations, causality loops do not represent an unpaid debt in physics, because the total energy and information content might remain invariant across the loop. The paradox is chiefly one of perspective. Our minds recoil at the prospect that there is no first cause. But within a self-consistent timeline, the loop might simply stand as a strange but permissible solution, an example of how a universe with time travel could be self-contained, with all its events linking seamlessly without external input. The cost is that it violates our usual sense of creation, inheritance, and progress, flattening them into a circle where everything that happens was, in a sense, always going to happen. These loops also provoke reflection on the boundaries of free will. If you are doomed to replicate the exact message you once received, can you choose to deviate from it? Could you insert a new sentence or omit a phrase? According to certain consistency principles, perhaps you cannot, or if you try, circumstances will conspire to prevent your deviation. Once again, we encounter the sobering notion that time travel might exist without affording us the ability to alter events in a meaningful sense. You might sit at your desk, pen in hand, determined to revise the letter you recall receiving. Yet each attempt to do so fails. You spill ink, or the phone rings, or you suffer a curious moment of memory lapse. The final message is identical because it has to be, and your fleeting sense of choice does not override the loop's integrity. Perhaps the most stirring aspect of causality loops is the existential question they raise about origins. We often trace genealogies of events, artifacts, or knowledge back through time, trying to find their inception. A painting can be traced to the artist who first conceived it, a novel to the writer who penned its words, and so on. But in a causality, that chain leads in a circle, never revealing a single point labeled, "Here is where it began." A loop of knowledge could, in theory, catapult societies forward technologically or culturally without any individual or group ever truly inventing the seed idea. This can evoke a mystical sense that, under certain extreme physical conditions, the universe might enable leaps in knowledge that appear to circumvent the normal processes of discovery or invention. For some, it is an unsettling reminder that logic and time's flow may not be as absolute as they seem. For others, it is an enchanting glimpse into the bizarre possibilities of a cosmos that remains partially veiled. The seriousness of causality loops extends beyond fiction into discussions among physicists about whether nature allows them at all. Many suspect that quantum effects, or the structure of space-time itself, might forbid stable loops from forming in the real world, thereby preventing the kinds of paradoxes they imply. Exotic solutions to Einstein's equations, such as those describing wormholes, raise the possibility of loops, but also often require negative energy densities or other hypothetical constructs. Some scientists invoke these extreme requirements to suggest that the engineering of a loop might be forever out of reach, implying that while loops are mathematically feasible, the universe places them beyond practical creation. Others remain open to the possibility that advanced civilizations or natural processes could generate them, producing phenomena that strike us as inherently paradoxical. If you let your mind rest on the idea of a loop, you might experience a gentle tug of wonder. Imagine the tension in your thoughts as you stand at the cusp of discovering that the book you are about to write was, in fact, the very text that inspired you in childhood, mysteriously delivered by a time traveler. You are both the author and the recipient, cause and effect. The sense of temporal orientation wavers, replaced by a cyclical perspective in which events fold back on themselves. In a meditative way, you might see all time as a tapestry of potential. Loops, small or large, some hidden from everyday view by the sheer improbability of traveling to the past. Now pause for a moment. Let this loop settle in your thoughts, as though you were holding that letter from your future self, turning it over in your hands, pondering whether you can break free of the script or if you are fated to send it on without alteration. Notice how this thought might make you question your belief that everything must have a discoverable origin. Also notice the subtle shift in perspective that occurs when you entertain the possibility that your future actions might be shaping your past. All along, the human mind thrives on linear stories. Causality loops ask us to consider a narrative braided into a cycle. With the stage now set, we approach the deeper workings of how such loops might be made physically real, if that is even possible. The solutions that permit time travel and, by extension, loops in the timeline often involve exotic aspects of physics, negative energy, exotic matter, or features of space-time geometry that remain purely theoretical. These concepts, arising at the boundaries of what we know, point to extremes that might be needed to hold open a wormhole or stabilize a closed time-like curve. Without them, loops could be no more than imaginative constructs. With them, we might find that the universe offers doorways to past epochs and the chance to inscribe ourselves into the timeline that created us. As we move forward then, our attention will turn to these exotic ingredients, negative energy and exotic matter, and the role they may play in holding open the gateways through which time travelers could pass. Are these materials truly feasible, or do they remain out of reach, forever confined to equations and speculation? Could discovering or engineering them open the path to consistent causality loops, thus placing us face to face with the reality of events that cause themselves? If so, would we be prepared for the philosophical and existential shake-up that follows? Exotic matter, as the name suggests, is not something you can pull off a shelf in a lab or mine from a distant asteroid. Instead, it is a hypothetical form of matter or energy possessing properties that defy everyday experience. One central property often cited is a negative energy density, implying that the energy tied to a region of space might register as less than zero, according to certain measurements. At first glance, this sounds impossible or contradictory. After all, in our normal world, energy is always additive. We sum kinetic energy, potential energy, thermal energy, and so on, never encountering a scenario where they sum to a value less than nothing. Yet in the bizarre underpinnings of quantum field theory and general relativity, phenomena such as the Casimir effect hint that negative energy densities could, under very specific conditions, be part of nature's repertoire. Negative energy density carries remarkable implications. In the standard geometry of space-time, gravity acts attractively, bringing masses together. Black holes, for instance, are so massive that they warp space-time to the point where nothing can escape their pull. Now, if you introduce a region of negative energy into that geometry, the equations suggest it could counteract that relentless inward pull. In effect, negative energy might push outward, propping open a space-time structure that would otherwise snap shut. This outward push is crucial for stabilizing the throat of a wormhole, the narrow passage that connects its two mouths. Without such a push, standard gravitational collapse would make the wormhole pinch off or degenerate into a black hole, thwarting any attempt at traversal. When physicists like Kip Thorne and his colleagues at Caltech began to examine the possibility of traversable wormholes in the late 1980s, they recognized that conventional matter wouldn't suffice to keep a wormhole open. Even the densest materials known would only add to the gravitational stress, causing the throat to close in on itself. So they posited the need for exotic matter, a form of energy or mass that exhibits a negative pressure or negative energy density. This exotic stuff, if it exists, would have the remarkable property of repelling rather than attracting, effectively shoring up the wormhole walls against collapse. Thorne and others used this theoretical scaffold to explore how one might, at least in principle, construct or stabilize a wormhole in the realm of general relativity. Such a notion inevitably stretches credulity. Even though quantum mechanics reveals that the vacuum of space is not truly empty, small fluctuations in energy can appear as virtual particles that pop in and out of existence, there is still scant evidence that we can harness or concentrate negative energy in a way that is both stable and large-scale. The Casimir effect, a phenomenon predicted by Hendrik Casimir, involves two closely spaced, uncharged conducting plates. Quantum field theory tells us that the plates exclude certain wavelengths of virtual particles between them, changing the vacuum energy locally. The result can be interpreted as a slight negative energy density in the gap. This effect, though real and measurable, is extraordinarily small and only appears in the presence of meticulously precise conditions. Extrapolating from such tabletop experiments to cosmic engineering tasks like building a stable wormhole throat remains deeply speculative. Yet speculation often drives scientific inquiry forward. If negative energy density and exotic matter could be produced or harnessed, the doors to advanced travel, both across space and through time, might swing open. A traversable wormhole, stabilized by exotic matter, would allow travelers to pass from one mouth to another without encountering the lethal gravitational tides that normally accompany black holes. And if one mouth of the wormhole were manipulated, perhaps by moving it at near light speeds or situating it in a powerful gravitational field, the differential in the flow of time between the two mouths might allow for the passage not only across space, but between different epochs. It is no coincidence that discussions about negative energy so often arise in the context of time travel research. At first, it might be hard to believe that the universe could harbor such bizarre materials, yet physics has surprised us before. Dark matter and dark energy, though not exactly synonyms for exotic matter, are prime examples of how we've come to accept unseen phenomena that shape cosmic evolution. Dark energy seems to drive the accelerated expansion of the universe, suggesting a form of energy pervading space that, in broad terms, exerts a repulsive influence. While the details differ, from the negative energy densities relevant to wormhole stability, the notion that our cosmos contains puzzling forms of energy is already established. Perhaps buried in the mathematics of space-time, exotic matter is another layer of that cosmic puzzle, waiting for the right theoretical and experimental breakthroughs to surface. Critics, of course, point out that there is a significant gap between the tiny vacuum energy fluctuations we see in the lab and the massive negative energy requirements demanded by a theoretical wormhole. Some physicists argue that quantum effects place stringent limits on how much negative energy you can gather and for how long you can sustain it, effectively preventing large-scale, stable wormhole engineering. Others hold a more open mind, believing that future insights might find ways around these constraints, much as we've discovered phenomena in quantum mechanics that seemed impossible in prior eras. The path from speculation to reality may be long, but it is not necessarily closed. Reflect for a moment on just how different our understanding of travel might become if exotic matter were discovered, or better yet, if it could be produced in controllable amounts. In an age when crossing interstellar distances remains unfeasible with chemical rockets or nuclear propulsion, a traversable wormhole would radically shrink the universe. Far-off stars could become day-trip destinations, entire galaxies potentially within reach. If the wormholes could be linked in a cosmic network, the philosophical impact would be no less profound. Humanity would discover that the cosmic stage is far more accessible, that our place in the cosmos is not bound by the slow trudge of subluminal travel. And indeed, if the wormhole construction allowed for time differentials at its mouths, we might stand at the threshold of traveling into the future or the past in ways that challenge fundamental assumptions of history, fate, and free will. One crucial implication emerges from this potential revolution. How do we handle the ethical and existential dilemmas of such power? If we can open wormholes or manipulate time, do we risk unraveling our sense of continuity? Do we risk causality paradoxes that, while perhaps resolved by self-consistency principles, would still rattle the normal progression of life on Earth? Exotic matter in this light isn't just a new fuel or building material, it's a gateway to tampering with the architecture of space-time itself. Our caution must match our curiosity, lest we unleash changes that we cannot fully predict. Then there is the question of whether the generation of exotic matter might cause new types of catastrophic events, instabilities in the fabric of space-time, that ripple outward with destructive consequences. The pursuit of knowledge does not always yield purely beneficial outcomes, as history has shown when humanity has tapped into nuclear power, genetic engineering, and other potent sciences. In that sense, exotic matter stands as a potential apex of advanced technology, seductive in its promises, ominous in its risks. For the moment, though, the conversation remains largely theoretical. We are far from being able to gather negative energy in amounts that would keep a wormhole throat open for even a second. But the conversation itself underscores the continuing expansion of what we consider possible, or at least permissible, in the realm of theory. By weaving together negative energy density, wormholes, and the notion of time travel, we glimpse a universe that might be far stranger than anything we've encountered to date. The edges of physics are reminiscent of mythic frontiers, calling upon our imagination to fill in the gaps that mathematics alone cannot fully illuminate. Those who study these possibilities acknowledge that they skirt the boundary of known science, stepping into territory where proven laws mingle with conjecture. But this boundary region is precisely where breakthroughs often occur. It is where Isaac Newton once found himself grappling with the idea of gravitational force acting over empty space, an absurd proposition for the science of his day. It is where Einstein ventured when his equations suggested that space itself could bend like a piece of fabric. The impetus to question, to test, and to dream beyond the comfortable sphere of existing knowledge has repeatedly led us to deeper insights about the cosmos. At its heart, the conversation about exotic matter and negative energy highlights a curiosity that we cannot help but indulge, a longing to know whether the constraints we experience in everyday life, distance, time's flow, mortality, are truly insurmountable, or if they are just the beginning of what we might achieve should we unearth the deeper strata of natural laws. Perhaps one day we will confirm that negative energy densities can occur in localized pockets, or we'll discover new quantum phenomena that simplify the creation of such states. We might refine our understanding of space-time so thoroughly that wormholes seem no more outlandish than black holes once did. Or alternatively, we may learn that the cosmos disallows stable, large-scale negative energy distributions, preserving the linear flow of time and the isolation of distant corners of space. In either outcome, the exploration itself enriches our conception of the universe. Let yourself pause here, allowing these ideas to swirl in your mind. Breathe in the sense of possibility, however distant, that advanced physics could rewrite the story of space travel and time travel. Breathe out the acknowledgement that much of this remains theoretical, a testament to the audacious spirit of scientific imagination. In that delicate balance between hope and skepticism lies the essence of progress. We have not proven that exotic matter or negative energy can be harnessed, but we also have not proven that they cannot. We exist in that territory where we must look to nature and see if it will in its own time reveal the secrets we ask of it. Now, as you reflect on wormhole mouths propped open by these hypothetical substances, recall that time travel discussions often pivot on such exotic constructs. The mental exercise of imagining strolling through a portal and emerging in a distant epoch or star system is powerful, stirring both our dreams and our deepest apprehensions. It reminds us that reality might hold wonders we are only starting to guess at, that the laws governing space-time might be pliable under conditions we seldom encounter on Earth, and it underscores that what we call impossible is frequently just a statement of our current limitations. With that in mind, gather your thoughts for a final moment of repose before moving forward. Notice how your perspective on reality may have shifted, even if slightly, by contemplating the notion of negative energy and exotic matter. The day-to-day world may remain the same. Gravity pulls us down, traffic lights shift from green to red, but the edges of our understanding have expanded to include phenomena so alien that they could reshape everything we know about travel, communication, and causality. Sometimes the greatest gift of such speculation is not to prove that we can achieve these feats immediately, but to remind us that the tapestry of existence stretches far beyond the visible horizon. In the concluding segment to come, we will leave behind the intricate physics and the labyrinthine paradoxes of time travel. Instead, we will turn inward and reflect on the philosophical implications of these ideas. How does entertaining the reality of time travel change the way we live today? What does it say about destiny, about meaning, about the stories we tell ourselves concerning our place in the universe? Embracing the idea that time can bend, or that we might harness exotic forms of matter, is not merely a question of engineering. It is a question of purpose and identity. By pondering these extraordinary possibilities, we can sometimes glean sharper insights into how we understand the present moment, the choices we make, and the shared journey of humankind through time. So, let us take one last breath here, inhaling the strangeness of negative energy and the glimmer of wormholes held open by forces that defy our everyday experiences. Exhale, acknowledging that even our most fanciful visions must submit to experimentation and rigorous logic if they are to become real. And with that gentle sense of closure, prepare to enter the final chapter of our exploration, the philosophical dimension, where we ask what it all means for the nature of our existence and the way we choose to spend our days in this vast, mysterious universe. Take a long, slow breath, letting your mind flow back over the paradoxes that formed the earlier stages of this journey. The grandfather paradox, the twin paradox, and others awakened us to how time travel upends our usual assumptions. They forced us to ask if the future can truly reshape the past, or if paradoxes simply mean that backward time travel must be prohibited. Yet as we ventured deeper, the concept of a multiverse arose, a grand tapestry of parallel realities, each with its own storyline. In this realm, paradoxes might dissolve because changing one timeline does not erase another. You simply step from one branch of reality to the next. The dreamlike vision of infinite universes beckoned us to imagine that every what-if spins out into its own dimension, intact and real. You then pause to contemplate causality loops, those closed chains of cause and effect in which an object or piece of knowledge creates itself. If you receive a letter from your future self and eventually send that letter back in time, you realize the letter has no clear beginning. These loops can feel comforting, as though the universe maintains an elegant pattern, but they also undermine our linear sense of origin. And woven throughout was the tantalizing possibility of wormholes, those theoretical tunnels in space-time that might facilitate leaps across both space and time, if only we could stabilize them with exotic matter or negative energy. Although such proposals remain speculative, they remind us that the cosmos might harbor astonishing phenomena we have yet to comprehend. In surveying these threads, you might find your sense of identity gently questioned. If time can loop back on itself, if multiple realities coexist, or if your actions in the present can ripple into the past, then who exactly are you? Are you a single, autonomous agent making free choices, or are you a character in a story whose ending is already fixed? Especially if Novikov's self-consistency principle ensures that all attempts to alter history end up fulfilling it instead. Is your sense of self anchored in the timeline you inhabit, or do you become one among many versions of you spread across parallel universes? A quiet tension emerges here, one that touches upon destiny and fate. If your every action in the past is somehow already written because you took it, the entire notion of changing history dissolves like mist. Perhaps your journey into the past is simply another part of an unbreakable sequence, leaving you to wonder if free will is illusory. The multiverse, in contrast, might let you shift to a new branch, rewriting events from one perspective, yet continuing them seamlessly from another. But even that begs the question of whether your core identity transcends these branches or fragments into multiple realities, each containing a version of you with its own path. There is a certain poetic unease in imagining that your choices are both infinite and yet inconsequential to any single timeline. The philosophical implications press upon the heart of what it means to be an individual in an incomprehensibly vast cosmic landscape. When you consider how destiny, identity, and morality intertwine, the possibility of altering the past or peeking into the future becomes an ethical mirror. If you had foreknowledge of tomorrow's events, would you intervene to prevent a disaster, even if it meant creating a paradox? If you could erase a personal regret from your timeline, would that undermine the lessons and growth derived from it? Or would you deem the pain a necessary part of your journey, shaping the person you've become? The mere idea that time might be subject to manipulation intensifies our sense of responsibility. Whether or not we actually can change the past, thinking about it urges us to re-examine how we value the present. Perhaps if you knew that time travel was real, your actions now would feel both weightier and yet strangely fleeting, knowing all could be revisited or undone, or that your future self might one day meddle in this moment. Such thoughts lead naturally to questions of purpose. Are we meant to yearn for dominion over time, to become masters of history and travelers to the future? Or is there something deeply human about living in ignorance of tomorrow and powerlessness over yesterday, anchored in a single unfolding present? There is a humble wisdom in accepting our finite experience, living life with the knowledge that each choice we make cannot be reversed in any practical sense. Even the existence of time dilation, which is scientifically confirmed, does not give us the power to move backwards in time. It simply allows us to observe that clocks run differently at high speeds or in strong gravitational fields, hinting at the plasticity of time without necessarily granting us the power to remodel events. Yet if future discoveries were to confirm some form of controlled time travel, how would we steward that ability? Could it unite cultures and eras, or would it become a tool for exploitation and chaos, rewriting events to favor certain individuals or groups? These reflections invite us to cultivate moral and philosophical maturity now, before any breakthroughs occur. We might need guiding principles for how to handle knowledge gleaned from the future, or how to respond if someone from the future unexpectedly arrives with urgent warnings. Such reflections may sound like fiction, but they ground us in the recognition that ethical frameworks often lag behind technological or scientific progress. By the time a practical time machine exists, if it ever does, will we have the wisdom to use it responsibly? In the end, the deeper message of these speculations might be found in the meaning we derive from the present moment. If time travel were proven impossible, life's richness and poignancy would remain intact. The ephemeral nature of each second passing unaltered might become more precious still. Alternatively, if time travel were someday mastered, we'd face a horizon of questions about how to preserve the dignity and value of each moment. The ordinary tasks of waking up, sharing a meal, or comforting a friend could feel both fleeting and eternal, overshadowed by the knowledge that somewhere, somewhen, these events might be revisited, or might already be happening again in a new branch of the multiverse. Let yourself rest in this contemplation, noticing how it stirs your sense of wonder, hope, and perhaps a little wistfulness. The notion that our cosmic tapestry could be woven from layers of paradox and possibility reminds us that reality is far from trivial. We stand on a small planet in an enormous universe, tethered to a flow of time we perceive as linear. Yet the tools of physics, philosophy, and imagination point to directions beyond that flow, hinting that the tapestry might be far more elaborate. You've considered the role of exotic matter, of closed time-like curves, of self-consistency principles, and of endless branching timelines. Each puzzle, each paradox, has led you gently into the realm of new perspectives, illuminating corners of existence not usually glimpsed in daily life. Returning now to this very moment, the only moment we can truly experience, notice your surroundings. You might hear the gentle hum of background noises or the subtle rhythm of your breath. Feel the flow of life in your body, the silent pulse that measures out each heartbeat. However far your mind has roamed across centuries and galaxies and hypothetical timelines, you are here in the present, where all the reflection ultimately resides. There is a quiet power in recognizing that, despite every enthralling speculation about rewriting the past or glimpsing the future, the gift of now is ours to cherish. And if, in some unimaginable future, we do learn to step outside the usual boundaries of time, we might come to see this present moment in an even more radiant light. Gently open your awareness outward, recalling that you've traveled a great distance in thought, from the simplest question of whether time must always flow forward, to the grandeur of wormholes and cosmic corridors, and finally to the philosophical landscape where the meaning of existence is called into question by the promise or impossibility of time travel. Thank yourself for the willingness to journey there, to expand your horizons even if only in imagination. Perhaps some of these reflections will stay with you, accompanying your daydreams and conversations, or emerging quietly when you watch a sunset and feel time slipping by. With a soft sense of closure, allow the final words of this exploration to guide you gently back to a place of rest. Time travel, whether forever out of reach or just beyond the next scientific revolution, invites us to appreciate the mysteries we have yet to solve, and it reminds us that the simple act of living, making choices, forming memories, loving others, and discovering who we are, has its own poetry and depth, whether or not we can loop back to change any of it. Embrace that lingering sense of wonder, and if you find yourself drifting towards sleep, let these questions cradle your mind like a lullaby. The notion that time is both precious and potentially infinite, that you are both bound to this moment and part of something larger than you can fully grasp. Return now to the here and now, where your breath flows, your pulse steadies, and the hush of this present moment envelops you. Thank you for joining this journey and allowing yourself to venture into the improbable realms of time travel and cosmic possibility. May the ideas you've encountered spark fresh questions about destiny, freedom, and the delicate tapestry binding all moments together. As you drift off to sleep, you carry the knowledge that the universe might be stranger than anything dreamt, by ordinary reason. And in that strangeness you might find solace and inspiration alike. Wherever your dreams may take you tonight, may you find comfort in the endless wonder of time.